Hello everyone, my name is Seunghee Han and I will present about our paper about preliminary evaluation of path-aware crossover operators for search-based test data generation for autonomous driving. Nowadays, autonomous driving industries became one of the most valuable industries. In this situation, safety assurance of vehicles became a key issue on development. To improve the safety perspective, several methods to test autonomous vehicles are developed. The common method is testing on real traffic, but real traffic test has safety risks in testing itself and it needs too much cost and time. So the virtual testing method has become a good alternative. SFERT is the one-off reset method to test autonomous vehicles in virtual environment. It has two main functionalities. Firstly, it can generate and evolve virtual road networks. Then, it can test the lane keeping functionality of autonomous vehicles. To achieve this objective, SFERT combines procedural content generation and genetic algorithm to road network generation and evolution. On the other hand, SFERT has some limitations, that is about search operators. However, these operators do not consider the road segment that was traversed by the simulation. So, objective of our paper is to refine limitations of SFERT by proposing novel crossover operators. The new crossover operators can utilize road traversal data on last simulation so that it can preserve the dominant traits of a parent road network. Moreover, we introduced new fittings function to capture more details of OBEs. Finally, we could produce road networks that maximize out-of-band episodes OBEs in simulation. Before explaining our main concept, I will introduce the way to create road networks. That is Procedural Context Generation, or PCG in short. PCG is a system that generates the virtual road network automatically. There are three steps to create random road network using PCG: road segment generation, and road network generation. And there are two validation methods: single road validation and road network validation. I will explain these methods briefly. The road network generation is an incremental process that builds road networks from road segment using PCG. First, it constructs a short straight road segment like A. And then it concatenates randomly generated road segments repeatedly until it reaches the map boundary. This is B and C. Finally, it generates and places multiple roads on the same map to create a road network like D. After generating road and road network, validation process is required. In order for a single road to be valid, a road must cross the map boundary and must not intersect itself. If a road violates one of these conditions, PCG rejects the road and generates another valid road. Next is road network validation. There are two conditions: all roads must have only valid intersections, and all roads must have at least one intersection. If a new added road violates one of these conditions, PCG rejects to add the road and generates new road until the road network is valid. The proposed ATEST, Automatic Test Data Generator System for Self-Driving Car, automatically generates test data map for self-driving car using GA. Our system inherits PCG and GA from SFERT with proposed improved genetic operators and fittings function. Within GA, we uses strategy of tournament selection and elitism mechanism.
As a fitness function, we use bounded lateral deviation. The fitness value is calculated as the distance between the center of the road and the ego vehicle. This lateral deviation is bounded by maximum half road width and counted as OBE if fitness value exceeds the half road width. The original SFERT string crossover operator generates child map using any roads within the selected parent maps. The join crossover operator, which is binary operator, gets any road within its parent map as input and splits each road into two roads at a randomly assigned segment. We cross-connect the divided road on the child map until the road reaches to the map boundary. If the child map including newly generated road satisfies the validation, add new road in the child map. Our ATEST join crossover operator operates at the path level so that only the roads actually traversed by ego vehicle could be selected. The traced path is shown at line in the figure A and B. The parent road is randomly selected based on the traversed path. Then the cut point would be selected from the parent road to retrieve the segment to perform crossover with. Figure A, for example, among the traversed path that involves the two roads, the road segment with yellow lane is selected to cross over. Likewise, the green lane is selected in Figure B. Then we cross-connect selected road segment until the road reaches to the map boundary. If the child map including newly generated road satisfies the validation, add new road in the child map. Otherwise, a test will make up to 10 attempts with the same pair of chosen roads with different cut points, after which it chooses another pair of roads from the parent. In Figure C, two chosen segments which is yellow and green lane are combined into child road and added to the child road network map tile. Join crossover process will repeat until the number of rows in the child map tile is equal to that of the parent map tile with fewer rows. This example clearly shows how our ATS join crossover operator logically improved from asphalt. Each red lane in the figure shows the path of the ego vehicle. Within the asphalt, since the crossover operates at the map level, the green lane in the middle figure is selected even though it did not contribute to the fitness value at all. This selection degrades the performance of GA because it's same as the random selection. To cut off this selection, we proposed a test operator that only the evaluated path of the vehicle could be selected. Where the selected road segment in the example includes the path. Since its fitness feature lies on its path, not on the map, we suggest that our ATS join crossover operator logically improve the asphalt join crossover operator. Similar to the join crossover operator, the original asphalt merge crossover operator also generates child map using any roads within the selected parent maps. Any road within parent is randomly selected, then each entire road is tested with the child map. If the child map including parent road satisfies the validation, add road in the child map. This method is basically only for the multi-road network. For merge crossover of ATS, it operates on the path that was traversed in the fitness evaluation. The traversed path is shown red lane in the figure A and B. While keeping the maximum number of rows to 3, ATS randomly chooses one or two rows that are traversed from one parent and merges them with the other traversed rows from the other parent. Then the chosen rows are merged into the child road network. The two blue lane roads from Figure A and one green lane road from Figure B are selected, which merged into child map in Figure C. After merging, merge crossover operator follows the same validation and iteration policy of join crossover. For the merge crossover operator, each lane in the figure shows the path of the ego vehicle. Within the asphalt, the blue lateral straight lane in the left figure is selected, even though it did not contribute to the fitness value at all. Same here, to cut off this selection, we proposed a test merge operator that operates on the path level, so that all the selected road segment in the example includes the path. We suggest that our ATS merge crossover operator logically improve the asphalt merge crossover operator. We did preliminary evaluation of ATS using Simulink Autonomous Driving Simulator. It resulted 13 to 29% more obvious than asphalt, and consistently outperformed random search. These early findings are in line with our expectation and shows its potential promising. In conclusion, we proposed more detailed fitness function and improved crossover operators in our system ATS, which is improved version of asphalt. Our fitness function eliminates the possibility of malfunction in the previous method and can capture out-of-bound episode more elaborately. Also, our new operators in ATS focus on the path traversed by the vehicle in the latest fitness evaluation in process of doing crossover. We expect our operators to better preserve the parts of the road network that resulted in each fitness value. Finally, through the preliminary comparison of ATS, we showed potentially promising performance. We believe more rigorous experimentation and comparison is future work. Thank you for your attention.